All right, so now it's time for our main presentation. I'd like to introduce my friend Chris Morisette, who is also members of the Houston Astronomical Club, North Houston Astronomy Club, and also FBAC. So he's got not just a dual citizenship, but tri-citizenship. So he's also involved at the Texas Astronomy Department. I know he deals a little bit out at Fort Davis there. You have a board position or something. In the past, you have held a board position. And he's also the novice chair at HAS. And clear nights, you'll find him either volunteering at the Georgia Observatory. He helps us out in the East Dome and has been one of the donors to help us purchase the new scope. And I've also done a bit of astrophotography with him at the HAS dark site. So without further ado, Chris Morisette.
All right.
We look forward to your presentation.
Yes, and in addition to the dark site, you'll also find me in Antarctica.
So that's even cooler.
That is a picture from Blind Bay on the Antarctic Peninsula. We are actually in the Antarctic Circle on that shot, and this boat that I'm on is surrounded by ice. It was amazing. If you ever get a chance, go. No dark skies. It's summer down there, so it was light all the time. So enough of that. So tonight we're going to talk about a little history. I love it when I can combine a couple of favorite pursuits, astronomy being one and history being the other. So what I've done is I've put together kind of my interpretation or quick overview, survey, if you will, of astronomy history. And so what I want to do today is talk to you about the objectives that I have for the presentation, go through the timeline itself, and then summarize at the end to see if we connected everything together. And then I'd like to show you the references that I used for the presentation. I'm not a professional historian, nor am I a professional astronomer, but I did do a fair amount of research, and so hopefully my citations and everything are accurate. I don't give you any misinformation tonight. So what we're going to do today, my objectives for tonight really are to identify the people and I qualified this a little bit, key people involved during our walk through time as it relates to astronomy. Not all these people are astronomers, but they are people that definitely contributed, in my mind, to kind of a fundamental change or understanding, and contributed to our understanding of astronomy. In doing that, I'll discuss key events and discoveries. And then again, I'm going to try to connect the past to the present because we're kind of in a golden age for astronomy. A lot of research going on, we're learning a lot. And I want to be able to demonstrate how we're standing on the shoulders of these people in our current pursuits. And then hopefully motivate you to further inquire and research on your own about astronomy and the history of astronomy. Now I got to put a couple of health warnings on this presentation. You're not going to see your favorites up here necessarily, okay? What I tried to do is I tried to select people that I thought fundamentally changed, altered our perception, our view, our knowledge of astronomy. So you're not going to see Charles Messier up here. Great guy, we love him. He contributed to our hobby in a profound way. But in my survey, I've got to pick who I wanted to go after. I've got some other individuals up here. Doesn't mean they're not important. Doesn't mean that others didn't contribute or weren't involved in some of the contributions that I'm going to talk about. But I had to fit 5,000 years of history in 52 minutes. So just a little bit of a health warning there. So here's the timeline that we're gonna cover during tonight's discussion, and it's my own concoction here. Dates and descriptions are all my doing here, but it starts out here. We're going to talk about astronomy and antiquity, Egyptians, Babylonians. We'll start out with Stonehenge. We'll then get into an area called the heavens demystified. So this is going to cover some Greek philosophers that really began to enhance our use of logic in looking at the night sky. We'll then talk about the geocentric model, perfected, and here Ptolemy's going to set the stage for us. We will discuss a little bit about the Renaissance and how that got us from a geocentric model to a heliocentric model. We'll then cover a period of time here called kinematic to dynamic. So this is all about, you know, we've accepted that we have orbits, circular orbits, elliptical orbits of planets and other objects in the night sky, but we'll really get into it and start to begin to answer the question, well, why is that? We'll talk about a broader cosmos, and here our good friend William Herschel will take the stage. We'll then get into a new understanding of physics in a broader universe, which was a couple of hundred years ago. And then from there, we'll talk about where we've been over the last 100 years, and also about a little bit about where we're going. So here's a timeline, the marker that I'll use throughout the presentation. And what I've done is I've, in addition to the astronomical notations here on the history, I've also included some other non-astronomy related historical events to kind of give you a little bit of a understanding of where we were at in time. So in this particular period of time, we're going to be talking about 3200 BC to, in antiquity, we're going to be talking about 600 BC. And what's happening during this period of time is really Egypt is becoming formed, it's becoming a great power, a great dynasty, and that's marked by the construction of the pyramid and the Sphinx, two well-known pharaohs of the time, Tutankhamun and Ramses. And then we also have Cleopatra down here at the end. Interesting factoid, Cleopatra, her family name was Ptolemy. And I thought, all right, I'm going to be able to link our Ptolemy to Cleopatra. They weren't related. It's a common name. It's sort of like Smith or Jones. So unfortunately, we didn't get that connection, but
I always wondered about that.
Quite an interesting character. So this is where we're going to start out. We're going to talk about astronomy and antiquity. And I've got my notes here, so if I appear to get engrossed in this, don't look behind the curtain at the man operating the levers. Little Wizard of Oz joke there. Yeah. So we'll start out with Stonehenge, and I've got a question mark around Stonehenge because there really isn't any conclusive evidence that this was in fact a structure that was geared for astronomy, or its main purpose was for astronomy. There were no written records from this period of time, unfortunately. But there has been speculation and debate about, you know, what Stonehenge has been all about. It has been discussed that this was a funeral monument that did include a celestial observatory. That the stones marked the rising and setting points of the sun at the solstice. So there is strong evidence from just those observations that in fact this did have an observatory function to it. There are, however, other functions to this. It was through our friends, the archaeologists, this monument here and the people that were that occupied it was deduced that this was a symbol of peace and unity, and also that this structure had certain healing powers because the stones actually have some acoustic properties that are rather unusual. Bottom line here is we believe this is the earliest example of an observatory, but we don't have too conclusive of evidence to make that assumption categorically.
It's not the earliest stone circle, however.
Yeah.
Those are in southern Turkey at a place called Göbekli Tepe, which means Potbelly Hill.
Mm-hmm.
But those things were buried, let's see, about 4,500 years before Stonehenge was built.
Okay. I did not know that.
Yeah,
So
they're the oldest structures we've got, and they are right after the ice melted in that area. I mean, within a couple of hundred years.
So this is the oldest structure that I'm aware of.
Oh.
Put that caveat out there. Anyway, thank you. Moving along, let's talk about Egypt. I think this is a particularly fascinating story here. The Egyptians did utilize astronomy for some very practical reasons and for some very mystical reasons as well. So practically speaking, there was an Egyptian calendar that was based on the movement of the stars and the planets. This calendar was used to fix religious dates for religious festivals, as well as fixing the hours of the night. The king's death was a really big deal, and the Egyptians did build their pyramids to align towards the quote-unquote pole star. Now, it wasn't Polaris due to precession. It was actually another faint star that was in Draco.
Was it Thuban?
Pardon me?
Thuban.
Could be. I wasn't aware of the exact name of the star, but that's where they aligned the pyramids towards. And they did this because the death of the king was really important. They wanted to ensure that his soul would rise to the heavens and he would become a star. Okay? And they wanted to do this for very practical purposes because they wanted to guarantee reliable flooding of the Nile, which in turn would give them a bountiful harvest. And this was really important because there were periods in time in Egyptian history where they didn't get the flooding and they didn't get the harvest that they needed in order to sustain society. And there was a lot of societal and political chaos that ensued. It was just not a very pretty time to be an Egyptian. So that was a big deal. They wanted to make sure that that king got up there and was able to guarantee this going forward. There were some practical benefits or uses for astronomy. One of the big, again, related to their calendar, one of the big things that they used astronomy for was to determine the annual flooding of the Nile. And this would in fact allow them to prepare for the flooding and get ready to conduct their harvest and make sure that they had the food to feed the population. They had a god that was personified the annual flooding, and he was a symbol of natural phenomena and annual rhythm. And he represented the order of the cosmos, and this god's name was Hapi, H-A-P-Y. So in Egypt, you had astronomy playing a pretty fundamental role, foundational role in keeping the order of their society together. In Babylon, they had some interesting uses and applications for astronomy as well. And Babylon, I think, being modern-day Iraq, is where we're talking about here. The Babylonians were alert to omens, such as lightning, thunder, things such as odd as sheep entrails and comets, things like that. If you saw one of these things, you were experiencing an omen, and that omen meant that something either good or bad was on the horizon. They also did a compilation of unwelcome events. So they kept records of famines, floods, earthquakes, plagues, things of that nature. And what they did later on in their civilization is they refined their prognostications of these unwelcome events by recording astronomical phenomena. So, so the movement of the sun, the moon, the planets were used as omens to predict these unwelcome events, and if you can predict these, you can prepare for them and minimize the impact. You might call this the first example of correlation without causation. I mean, obviously these events were not going to be a cause of a certain unwelcome event, but they did act that way and use that information to try to make predictions. And again, by virtue of their study of the heavens, we're able to push forward our understanding of astronomy. So that's antiquity. So now we'll move into this area of time called the heavens demystified. And this covers roughly the period of time from 600 BC to 100 AD. And here are four principal characters that I thought were unique and had something interesting to contribute and say during this period of time. We'll talk a little bit about Pythagoras, Aristotle, Aristarchus, and Hipparchus. These are 4 Greek philosophers during this period of time. All but one was born in Greece. The Hipparchus was actually born in modern-day Turkey. So what did these individuals do for us? They should have helped me get, or should have, I wonder if they worked on a laser pointer. Ah, they did. So using a little of the Babylonians, I predicted.
Channeling the Babylonians.
I got a good, yes, I got a good omen there. Okay, so Pythagoras actually, go to my notes here so I don't get off script. He actually proposed a solar model of sorts. Now he had the sun still orbiting around a central core of fire out in the heavens, but he did propose a quote-unquote solar heliocentric model, if you will. Not entirely heliocentric. He assumed that there were circular paths for the objects that were orbiting the center, and he also assumed that these objects were spheres. And he also realized during his course of study that Venus was both the morning and evening star. So those were the contributions of Pythagoras, at least in my short survey of history. Aristotle was an interesting person. Here's where you really begin to see some logic and quote-unquote demystification happening in our study of astronomy. He argued that celestial objects were spheres, and he went farther and said he was going to provide proof that they were in fact spheres. So here you see where here's a picture of a lunar eclipse from a while back. He argued that because of the shadow of the Earth on the moon, and it doesn't show up very clearly in this picture, but you can see there's a bit of an arc or circular form to it. And by witnessing lunar eclipses, he argued that in fact our own Earth was a sphere. He had other methods for buttressing that claim. One I thought was pretty cool was when he observed ships coming over the horizon, he would observe the mast of the ship coming up first and being visible, then the deck of the ship, and then the hull of the ship. So he was making that assumption, that observation, that it was coming up over a large sphere of some sort. But that was Aristotle, and I thought that was a pretty profound use of logic, and that's where we begin to use logic in history. Aristarchus was a pretty interesting guy too. He was using basic geometry, trigonometry, and applied that to find the relative dimensions of the solar system. Now, I'll show you his predictions on the next slide, and they're off, but he did use these to conclude that the Earth is much smaller than distances to other objects. And that was, again, a pretty profound discovery, assumption, using some pretty crude tools at the time. There were no telescopes at that point in time, so he didn't have the benefit of modern technology. Hipparchus had discovered precession, and he also prepared a stellar catalog that Ptolemy and others used in the development of their own written documentation. Here's
Chris,
yes.
Questions?
Yeah.
On the previous slide,
Yes.
on Pythagoras' diagram, it says counter Earth and Earth.
I'm sorry?
It says counter Earth and Earth. Is on the
Counter Earth and Earth. He's wondering what on Pythagoras.
Oh, here?
Counter Earth and Earth.
Oh,
He's wondering what that's about.
I'm not sure.
Okay.
Good catch, though.
Well, it sounds like he thought there was maybe a counter to Earth. Is what it sounds like. So
yeah, I don't know, but good call. Any other questions? Yeah, help me out if there's questions. Yes,
Hey,
sir.
Chris, got a question here. Dr. Farkas, wow, precession. In your research, did you pick up how he identified the concept of precession?
A little bit. He actually did go back and have access to some records or folklore from previous observers, and from that was able to make that conclusion.
That is cool.
Yeah, you know, how do you do that? And you would have to have that information
Okay.
in order to draw any conclusions like that. So here's what Aristarchus predicted, and this is, you know, in radii. So you got to read the left-hand side here. So the sun's radius and Earth radii, he had, you know, roughly 7, and today we know it to be 109. It was way off, right? Here he did a pretty good job. Earth's radii and moon radii. I mean, 2.9 versus, you know, 3.7. That's pretty darn good. And then here again, Earth-Moon distance. He was off by, you know, a factor of 3. And then, of course, Earth to Sun, he was way off. But I think the important thing to say here is that he recognized that the distances between us and other objects is way, way larger than the size of our own. And that's really the message I was trying to get through. But still, pretty incredible nonetheless. Okay, so now we're going to move on in our timeline. We're going to talk about the geocentric model perfected and then the heliocentric model. Here, this period of time, Egypt was actually had a Greek occupation, a Greek running of affairs of Egypt during the latter part of the last millennium. So Ptolemy was Greek. Cleopatra actually was Greek. Hellenistic, I think, was the term, and so that's why you see that. Anyway, but during this period, and then the Romans, Cleopatra had a very colorful life. She was involved with Julius Caesar and Mark Antony, and after everything kind of fell apart there, the Romans came in and took it over. Egypt, that is. About this time was really when Egypt hit its, kind of hit its height, and then a mere 300 years later, 350 years later, it fell. At least the western half did. The Renaissance is really something that I want to point out here. This is really a key event that kind of spurred on the heliocentric model, and I'll talk about that here in a second. So here's the geocentric model, and this Claudius Ptolemy was the principal character in this story. He was an astrologer, so like the Babylonians, he was looking for ways to predict either good or bad events that might come up on the horizon. So he was particularly anxious to know the position of the planets at all times. And what his model did, and it was based on the Earth being at the center of the world and everything else revolving around it, what he tried to do is put together a model that made those predictions. And he used some tools, whoops, all right. He used some techniques here that allowed him to show the retrograde motion of the planet. So you have here this thing called an epicycle, which is a small orbit that a planet makes around itself, or around a certain point here that sits on this thing called a deferent, which is a larger circle, which we would consider today to be an orbital circle. He used this other technique or tool, or whatever you want to call it, called an equant, which is really involved with this the offsetting, if you will, of the center point of the deferent. And he used that to enhance the effect of eccentricity of the orbit of a planet, and flatten out that retrograde motion so that it was more in line with what they observed what he would observe when he went outside and viewed the heavens. But that was his model for predicting the position of the planets in relation to Earth. And it was, his model did not rely on knowing the distances like Aristarchus was trying to do, but rather was just based on the observations that he was making. And it was obviously flawed because, you know, the planets don't revolve around don't orbit the Earth, they orbit the Sun. But it was a good model to make predictions.
Could he predict like conjunctions?
I'm sorry?
Could he predict conjunctions?
I don't know. You mean like opposition and that type of thing?
Well, you know, like the moon coming close to Jupiter, or Jupiter and Saturn coming close.
I don't know. But that was his model, and again, it was flawed. But but it stood for over a millennium. I mean, this model and its use were in vogue for, you know, until really the Renaissance. In addition to the model, he also did our, you know, astronomers of the future a big boost, a favor, laid a foundation by I'm not doing that, by authoring this document called the Almagest. And in here he had astronomical information about the movement of the sun and the moon and the 5 planets at the time, and the fixed stars. And this book was, you know, this book had 13 different sections, and covering these areas of astronomy inquiry. And his book was based partly on Hipparchus's star catalog. So I mentioned earlier that Hipparchus had actually put together some writings on this, and Ptolemy made use of that. So here again, he had a model. It did work. It was flawed, but it did contribute. He did contribute to our understanding of the heavens, and this was something that formed the basis for future astronomers. Okay. So now we'll move on to the heliocentric model. So I mentioned earlier that we had the Renaissance, and the Renaissance was really an active time to really question and go back and really, not only in astronomy, but just about every other endeavor of life. It really marked a time of critical thinking. And there was a lot of dissatisfaction with the geocentric model because while it was useful, it didn't describe reality. And so along came these individuals here, Copernicus, Galileo, and Kepler. And again, there are others. Don't want to shortchange those folks, but these are the 3 that really kind of, to me, marked some you know, important changes in our understanding of astronomy. So Copernicus was, what he did is he really he assumed that we have a heliocentric model, a heliocentric way of operating. And by doing that, he was able to describe planetary motion without epicycles. It just changed, it simplified, changed everything. Now he published his results about 2 months prior to his death, and it was probably a good thing because to advocate for a heliocentric model during this period of time could be kind of dicey because the church was very invested in the geocentric model, in the primacy of man and earth, and to go against that could be heretical. So Copernicus kind of, here's my exam paper, I'm out of here.
A good time to exit.
And Galileo was left to kind of go out and provide some observations that buttressed his assumptions. And Galileo was the guy that took the heat. He was the first, just among other things, he was the first astronomer to, or first person to make astronomical observations using a telescope. So that was one claim to fame. But his observations of the moons of Jupiter, the Galilean moons, showed conclusively that not all objects orbit the Earth. I mean, there was just no ifs, ands, or buts about it. So there again, it was great. It was further proof, evidence that the heliocentric model really is the model that we ought to be following. But again, he had to deal with the church, and he was able to successfully negotiate around that, but I'm sure it wasn't a pleasant experience. Moving along, Kepler. Kepler was really the discoverer of the laws of planetary motion. He had shown using quantitative methods that we actually have an elliptical orbit, and that speed variation, the speed will vary of a planet going around the sun that speed will vary. And he also demonstrated, again, using quantitative methods, the relationship between orbital distance and orbital period. His laws actually explain the orbital speed variation of Mars, which had been kind of a puzzle throughout the course of history. So this is kind of the first example I saw where there was some quantitative meat put on the bones of astronomical study. And so these are the three principles here that were involved in getting us to a heliocentric model. And again, this is happening in and around the Renaissance. So now we move into a couple of different epochs here, periods of time rather, kinematic to dynamic and a broader cosmos. Before we do that though, this is great. Look at Harvard. Harvard was established in 1636. The Harvard that we all know and love today. Well, we all know, put it that way. It was established before Louis XIV took the throne of France, before the Glorious Revolution, which is really when the British became more of a constitutional monarchy, the American Revolution, the French Revolution, and the Napoleonic Wars. I think it's kind of wild. Anyway, I waxed nostalgic. So kinematic to dynamic. What is this guy talking about? So there was some dissatisfaction with divinely inspired orbital paths. In other words, why do the Earth, Moon, and planets follow orbits? What's the reasoning behind that? What's the logic behind that? And so a couple of principles that I identified here really moved forward our understanding of that. The one person, Robert Hooke, I'd never even heard of before I started to study this. Hooke showed that a central force leads to an orbital motion. He studied pendulums, which I tried to kind of show over here. And his observations of pendulums didn't directly, he didn't use that information directly to formulate his theory, but those observations and his understanding of governing principles indirectly influenced his formulation around orbital motion. And I'll talk a little bit more about that here in a second. Isaac Newton, if we've all taken a physics class, we've all heard of Isaac Newton. He had developed the three of Newton's laws. I've got here in my notes, he discovered gravity. I think that's true. I'll have to go back and look at my citations, but he certainly used gravity in his laws. And the three laws are stated as the first law of Newton's was every object moves in a straight line until it's acted upon by a force. The second law is the old F equals ma. I got a kind of a funny story there. I was trying to learn how to water ski, and my roommate's father owned the boat, and he was an engineer from way back, and I kept falling. And he came around and he said, I said, Bob, what do I do here? And he goes, remember one thing. And I go, what? And he goes, F equals ma. And I said, that is not helping me. Anyway, kind of a fun story. And then the last one here is for every action there is an equal and opposite reaction.
Now, I believe people, knew that there was, something pulling down. Newton was the one who realized that it goes all the way out to the moon. That it's not just like local to the Earth's surface. It's astronomical too.
Okay. Thank
Because
you.
Galileo, he played around dropping balls and things.
Yes, correct. Okay, good. I appreciate that.
Hey, Chris, you have a
Yeah.
question here or comment?
Yeah,
Yes.
just a little bit of trivia. I'm glad you brought up Robert Hooke. Newton's famous quote about standing on the shoulders of giants was actually, they think, sarcastic dig at Hooke.
Okay.
Newton and Hooke did not get along.
Yeah, they had some
It's
issues.
an understatement.
They had some issues for sure. But I thought what he did was pretty fundamental to what we're
Yeah.
talking about here. So let's talk a little bit about what Robert Hooke did. And forgive me for reading off these slides, but the quotations and the verbiage is probably better than I can do ad-libbing. But Hooke, he said that the orbital motion of a planet is determined by compounding its tangential velocity with the radial velocity impressed by the gravitational attraction to the sun. So what you see here is a diagram from one of his papers, and he's showing here the tangential velocity, which is represented by this segment, the radial velocity, which is represented by this segment, and then the resulting angular, let's try to have that right, the resulting angular motion. So he was thinking through, how does this circular path really come into being, and that was what he was working on during this period of time. And then you had Newton, and Newton obviously did way more than what we were concerned about in terms of orbital motion, but his second law dealt with forces in circular motion and the force of gravity. So here again you have Newton playing a big role as well. And here I'm trying to bring it all together, and let's see how this fits. So Hooke proposed the idea that celestial bodies, such as planets, were held in their orbits around the sun by a force inversely proportional to the square of the distance between them. Newton formulated his law of universal gravitation, stating that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distances between the centers. This law Newton's law provided a mathematical framework for understanding not only terrestrial motion, but also the motion of celestial bodies. And then to just sum up here at the bottom, Newton's three laws, especially the first and second, provided a theoretical foundation for understanding how objects move under the influence of gravitational forces, including orbital motion. So back to the original point of inquiry, people weren't satisfied with assuming that these bodies had circular motion. They wanted to understand why, and I think Hooke and Newton really took us to that point. So that was our age of kinematic to dynamic. Now we get into an area that I love. I think I call this a broader cosmos. And this individual here, William Herschel, he is the most, what do I want to say, unbelievable astronomer that nobody's ever heard of. This guy was unbelievable. Typically if you're good as a builder of telescopic equipment, as an observer, or as a theorist, if you're good in one of those three silos of fields, you're great. If you can do two of these, you're exceptional, and if you can do all three, it's really unheard of. And William Herschel really did excel in all three of these areas of endeavor. So let's talk a little bit about how he contributed as a builder. And I'm talking about William Herschel on all these slides. That was one of the changes that I made to the pack, but I'll talk us through that. So he over the course of his lifetime, he constructed 73 telescopes. He fabricated mirrors of various for various focal length telescopes, and here are the numbers of mirrors that he actually put together. He performed and recorded over 2,100 experiments on telescope construction. Not astronomy, just telescope construction. And he constructed and delivered telescope for royalty and dignitaries throughout Europe, one of them being Napoleon's brother. So as a builder, he was unbelievable. As an observer, he was unbelievable. So he made the first discovery of a planet since antiquity, which was Uranus. He also, as an example, he also had many observations of solar, lunar, and planetary observing. He determined the height of mountains on the moon. He determined that Mars had an atmosphere and that Jupiter had rotation and winds. In his observation of periodic stars, he measured the periods, the maxima and minima of their brightness. It was truly astounding. In review of the heavens, he discovered 106 new binary stars. Did a lot of observing of double stars, and he had put together a new catalog of new nebulae and star clusters. The one quote I like here is that, and this is Herschel, upon receiving a copy of Messier's catalog, he said, "Several nebula might yet remain undiscovered." So he was definitely active in going out and observing and discovering new objects. His 3 catalogs cataloged around 2,500 objects, and 138 of which were previously known. So he was very active in going out and finding new deep sky objects. Now, let's go back. Okay. Now, here's where he really brought it all together as a theorist. So in his, and these titles that you see up here are the documents that he authored that contain these bullets that I'm going to talk about here. But he actually mapped the Milky Way via a technique called gauging, and that is where he was going out and looking at the star densities out in the night sky. He was able to get the shape of the bulge and the disk of the Milky Way correctly, determined that the sun was in the galactic plane and that we were offset from the center of the galaxy. And he suspected that not all nebulae are star clusters. And he really started to dig into this whole business on nebulosity in stars in this publication here. He discovered and studied this planetary, I'm having a, Jeff, help me out, the Ring Nebula, planetary nebula. Yes, that's not the Ring Nebula, but he studied this planetary nebula and was trying to resolve this, the gas and everything down to individual stars. And he wasn't able to do that. He got down to the white dwarf at the center of this thing, and he noticed a symmetrical cloud around it. And he came to the conclusion that, after studying this, there really must be objects that are true nebulae. In the shining of light, he asked the questions: is the central point is a star? Is it forming out of fluid? Is gravity working on the luminous matter of the star? So he's beginning to think about, star formation as we know it today. And then down here, this is a quote from on nebulous stars. The stars are forming these extraordinary nebula by some waste of nature and are no longer fit for their former purpose, and they unite into a new body. So what he's talking about here really is the death and dissolution of a star. He was he didn't state it as we know it today, like a supernova or planetary nebula formation, but he was really beginning to hone in on, you know, the life cycle of a star. And in his last thesis, Construction of the Heavens, here he really lays the foundation for modern physics, astrophysics. He says that nebulae are not permanent bodies, and that stars actually go through a life cycle. And here are the steps that he had for the life cycle of these stars. It's not right. I mean, he talks about globular clusters devolving from a galaxy and so on and so forth. But down here at the end, he begins to really hit on something. He said, nebulae are the parents of stars. A new star is formed and the process repeats. So he was a little bit wide to the right with his field goal, but he was on to something. And I think he was on to something very profound here. And if you think about it, it really kind of sets the stage for where we're at today.
Didn't he believe that originally everything could be resolvable to stars if he could zoom in or get enough magnification? And later on, he admitted his mistake when he discovered that, hey, there are such things as nebulae and they're not.
Yeah, and it was right.
Yeah.
It was this paper.
But originally, he was adamant that everything could be resolvable.
He was,
Yeah.
and he was adamant in that way because he was looking at some of the things that were in the Messier catalog, and he was able, through his construction capabilities, he was able to actually resolve stars.
And he was looking at things at ridiculous magnifications like 900 or you know, really high magnifications.
I think there were some globular clusters that that were classified as something other than a grouping of stars, and he resolved those stars. It was one of the things, I can't remember exactly which one, but anyway, it's an amazing story. I love it. Okay, so moving along here, cute, you know, get the hook if I'm running too late. So now we get into a new understanding of physics in a broader universe. And again, here we're talking about 1830s down to 1930. Now I'm going to make an honorable mention that there's a person that's not on the list here, but a person by the name of William Huggins. He actually identified, in 1862, identified chemical elements in stars. And he was able to do that by taking their spectra and matching the wavelengths of the atoms measured in laboratories against what he saw in his observation of stars. We use spectroscopy so much in our endeavors in studying the universe and the stars that I wanted to give him a shout out. Okay. Now, here we're going to talk a little bit about Albert Einstein and Edwin Hubble. Einstein was unbelievable. Here you had this very unassuming, innocuous man sitting in his apartment in either Bern or Zurich, I can't remember where, doing these thought experiments that, I mean, they changed the world, literally changed the world. And so here's what you see. I've taken his general theory of relativity and just kind of busted it down into some of the key findings that he developed, and not from his thought experiments, because they didn't have any observational. There was no observational backup at the time he developed this theory. There was later on, but not at the time he developed it. So here you have the curvature of space-time. This is all about matter curving space and causing bodies to move in ways attributed to gravity. Here you have gravitational lensing, where the gravity of an object was so large and powerful it would actually bend light around it, so that if you had two stars that were obstructed by, say, the sun in this case, and you had a solar eclipse, you could actually view those stars even though they were physically behind the sun. His theory also predicted things like black holes that you see over here, and you have gravity waves that were also predicted by general relativity. He also, his general relativity also predicts that there is an expansion of the universe as well. So, I mean, it's amazing. How does anybody do that? I mean, it's unbelievable when I think about it. But this is what he postulated, and all these things became verified in our scientific endeavors over the next 100 years. It's truly fascinating. And before I get to Hubble, that's a fundamental shift in our understanding of physics. We had Newton as our model for physics. Einstein really just turned it up on its head. Yes, sir.
And I've always thought that it was even more amazing that he did all this with no experiments.
Yes.
This is just all in his head and on his paper and pencil, And how did he do that?
I know. It's unbelievable. So what did William Herschel provide, or not William Herschel, but Edwin Hubble? Why is he up here? Well, I think his discovery that proof that that Andromeda actually was not a nebula within the Milky Way, but rather a distant universe or distant galaxy. They didn't have the term galaxy at the time. But his use of Cepheid variables to show that this spiral nebula was actually a galaxy far from Earth, or far from the Milky Way, and that really, lended proof or provided, I think, a wider view of the cosmos than what we had before. He also, through his observations, determined that the universe was expanding. So here he was adding, observations data, if you will, to buttress the general theory of relativity. And I think these two individuals really kind of set the stage for the last 100 years. Gravitational lensing has been used to study distant galaxies and even detect exoplanets. Black holes went from a mathematical abstraction to an observed and studied object phenomena across the universe. Gravitational waves, first detected back in 2015, opened up a new era of astronomy, new way to study cosmic phenomena. And then I think together Einstein and Hubble laid the groundwork for the Big Bang theory and our understanding of cosmic expansion. So again, two really important individuals in furthering us along the astronomy timeline. Okay, so now let's wrap this baby up. Talk about exploration and discovery accelerated. There are so many astronomers over the last 100 years that you couldn't even list them here on one or two pages. Carl Sagan was always a favorite of mine, but when I looked at him in comparison to what some of these others did, I picked out 4 that I thought were worth mentioning. So I'll go through these individuals very quickly. So you had Chandrasekhar, whose Chandrasekhar limit of approximately 1.4 times Samantha's sun was critical for our understanding of the evolution of stars. You get over this limit and you can get to a neutron star or a black hole upon the death of a star. Vera Rubin provided evidence for the existence of dark matter through her observations of galaxy rotations. Stephen Hawking, he was notable for the theoretical prediction that black holes emit radiation. And then Jocelyn Bell, who co-discovered pulsars, and that revolutionized our understanding of neutron stars. So again, there's so many to list and talk about, but these are the 4 that I thought were worth mentioning here in the presentation. So over the last 100 years, we've gone a long way. We have obviously the space age hit in 1957. That opened up some big horizons. We had, Mariner as an unmanned mission to go around some of the planets. Of course, the Apollo program put feet on the ground on the moon. Viking, Voyager, Juno, Cassini. I mean, there were a lot of things that came to the fore here once Sputnik got off the ground. We had a discovery of the cosmic microwave background by the 2 Bell lab individuals, Arno Penzias and Robert Wilson. Kind of discovered this all by mistake and accident, but again, a very important discovery. Space telescopes and observatories, Hubble, James Webb, unbelievable there. Exoplanet discoveries, that's kind of a new thing that has really opened up our eyes about worlds that are beyond our own solar system. Dark matter and dark energy are kind of new frontiers for us to study and understand, and then gravitational waves, again, another important finding that we've had over the last 100 years. Looking forward, you know, here are some kind of big headers or placeholders for a study that we have going on, exoplanets, use of, you know, looking at and see what kind of atmospheres these have. This topic called new messengers, which really deals with how we can use gravitational waves, neutrino bursts, things like that to study more about the universe. The list kind of goes on and on and on. I'll spare you the details here because I think we're kind of running late on time. But that's what we've got teed up for the next decade or so, and pretty exciting times. So let's kind of recap here. We'll just do a quick summary of where we were at. Ancient civilizations used astronomy for practical and mystical purposes. Greek philosophers brought rational thought to our understanding of the heavens by attempting to describe the nature and size of the solar system. Ptolemy perfected the geocentric model to provide accurate positions of the moon, sun, and the planets, and left a lasting written record. Renaissance astronomers like Copernicus, Galileo, and Kepler upended the geocentric model with the heliocentric model. Newton, with help from Hooke, I'll give some props to Newton there, provided a quantitative and predictive explanation for gravity and orbital motion. Herschel laid the foundation for modern cosmology by unveiling a broader cosmos and by laying out the nature and relationship between stars and nebulae. The theory of relativity provided a new understanding of physics, together with contributions by Herschel and Hubble that really set the stage of astronomical inquiry over the last 100 years. And then during 2020 to 2030, these areas of inquiry will be further developed and expanded. Here are my references. We had a great presentation by Larry Mitchell here a while back. I drew heavily on that. This is a really good book if you want to know more about William and Caroline Herschel. And his sister was very influential and did a lot of work and was a good astronomer, great astronomer in her own right. Other books that I'll just leave up here for the list. Highly recommend these. And with that, I thank you. And I'll take any questions if you have.
You know, when Einstein got his Nobel Prize, they did not list the general relativity as one of the things
Really?
he did.
Yes.
Because they thought it was too controversial.
Exactly. I went to the Nobel Prize Museum in August, and yes, that's exactly right. They didn't award
Brownian
him.
motion, right?
They didn't
No.
The
award him.
photoelectric effect.
Yes,
Photoelectric
that's
effect.
correct. Because it was less controversial.
Yeah.
And
And
they
it solved a puzzle that people had tried to work out, and nobody could do it.
And they never gave Gandhi a Peace Prize.
Yeah.
Well, he got killed, so. they don't
Well,
give it to
no,
dead
while he
people.
was alive, he was up, and again, it was like one of these things where, well, we don't want to do, anyway, I can go on and on. Yes, correct. Yeah, that's a good point. All right, well, thanks for your attention.
Yeah, I would highly recommend